I'm Professor Brad Fulton, and welcome to my Stats podcast. This is an edited audio recording of my course. Each lecture is its own episode, and there's a total of 24 lectures. This course provides an introduction to the quantitative methods social scientists and data analysts use to collect and evaluate empirical data about society. Through this course, you will learn to gather, describe, and analyze data with an emphasis on the application and interpretation of these methods. This course will also help you to be a more informed and critical reader of academic research, public opinion polling, and advertisement claims that present statistical evidence. Although some of the current events I reference might be dated, the content is timeless. I hope you enjoy this lecture, and if you have any questions, you can email me at bradrfulton@gmail.com. Hi, my name is Professor Fulton. If you like this podcast, you'll love the book I use for the course. It's titled Statistics, Unlocking the Power of Data. This book uses a highly intuitive approach to help students visualize statistical concepts, which accelerates understanding. I've reviewed dozens of textbooks, and Unlocking the Power of Data is hands down the best one out there, mainly because of its unique intuitive approach and straightforward explanations. You can find a link to the textbook in the show notes, and if you use the promo code BLOCK5, you'll get a 10% discount. The first thing I want to highlight is the two methods that we've been learning for calculating confidence intervals and the two methods for doing hypothesis tests. And it's important to know the differences between the two, but also how they're tied together or how they're related. So for calculating confidence interval, the only difference in the two methods is how we estimate the standard error of the test statistic. Throughout this whole course, the critical unknown value is the standard error of our test statistic. So like we have our sample, let's say we're doing mean, we know the mean value of our sample, we know the standard deviation of our sample, but what we don't know is the standard error of our sample. And that's critical for doing confidence interval and hypothesis tests and all of that. Can someone take a stab at interpreting what standard error even is? When we talk about standard error, what is that measuring? The key thing is this is critical in statistics because we only have a sample from the population. And if we sort of re-pulled from the population a new sample, the new sample means it's going to be slightly different from our original sample. And so what we need to find out is how much those sample means would vary from sample to sample. And we've seen that from whether we're doing sample means all the way up to regression, that because we're only taking a sample from the population, we need to take into account how much that sample would vary from sample to sample. And that's what standard error measures. And so if you think about it, standard error is measuring how much error is in our sample. We've learned two methods for calculating the standard error. Before I do that, there's a third method, which is just simply doing it, like taking 1,000 samples. So I guess technically we know three methods. We probably would never do it in practice, but it's important to know that you actually could go out and take multiple samples, take multiple sample means, and there's characteristics associated with that approach as well. So, but what we learned was bootstrap simulations, which simulates taking multiple samples. And a key thing with bootstrap is where are we getting our data to do bootstrap simulations from our observed sample. So let's say we have sample data and we're getting our test statistic is sample mean, and then we do bootstrap simulations. And so the bootstrap simulations is going to construct a sampling distribution of sample means. What's going to be the mean of that distribution? So we have a sample, and this is the X bar value. So this is one sample, so we have our X bar. We're going to do bootstrap simulations, which basically pulls data from our observed sample and does it with replacement to generate a new sample. And then we're going to do that 1,000 times such that there's a distribution of sample statistics, a distribution of sample means. So the center point of this sample was 6. the mean value of our sample is 6, and we're going to take multiple samples from our observed sample. What's the average or the mean value of all those thousands of samples going to be? 6. This is important to sort of have this down. U equals 6.1. So this is bootstrap sampling. If we were going to do the method of just physically going out and taking 1,000 observed samples that are, same sample size as this one, and then we calculate the sample statistic for the 1,000 that we actually physically went out into the population and did, what would the mean value of this distribution be? It's 6.1, and the main thing is that this is typically not known, but if you did go out and do enough samples, and really doing enough samples means you're sampling the whole population, the mean of the sampling distribution is going to be the mean of the population. Whereas this one, when you do bootstrapping, you're sort of constrained by your original sample of what you have as your mean, but you know that that's a pretty good estimate of the population mean, but they will produce slightly different results. And so in regards to standard error, you assess the variability of the test statistics, i.e. its standard error, by creating many bootstrap test statistics. So this is going to be a distribution of many sample means, and we want to know the spread of this distribution of sample means, how they vary by sample, from sample to sample. And so with bootstrap simulations, the way we calculate the standard error for this sample is the standard deviation, or the spread, of our bootstrap sampling distribution. So then formulas based on theoretical distributions, the way that works is there's mathematical theory that says if you have a large enough sample size, they can predict what the distribution of sample statistics is going to be. And they say, we know that if you have a large enough sample size, the distribution of these sample statistics will be a normal distribution. It's not a coincidence that the distribution from the bootstrap simulation looks just the same as the distribution from what theory would predict that it would look like. It's a normal distribution where it has a mean and a known standard deviation. It's going to follow a normal distribution, and that allows us to then say, well, then we can use specific formulas to calculate the standard error. And that's where that one page on the review lecture just has, here's all the formulas for calculating the standard error. And it's solely because of mathematical theory says that the distribution will be more or less like this. And if it's like this, then we can use these formulas. But if the sampling distribution isn't like this, like if you have a really small sample size or other sort of conditions aren't met, then you can't use the formulas. You would have to do bootstrap. But for the situations that most of them that we look at, it meets all the conditions. And so that's why you can either use the bootstrapping or the formulas based on the theoretical distributions. So you use a formula to calculate the standard error of the test statistic, and then use the normal or the t-distribution to find z star or t star. Really, in bootstrap simulations, we don't use any formulas. There's no formulas for calculating what the standard error is, because you just have a series of 1,000 sample statistics and you just calculate the standard deviation of that distribution. This also relates with doing hypothesis tests. We learned 2 ways to conduct a hypothesis test and obtain a p-value. And again, it's the related difference is in how we estimate the distribution of the test statistic, assuming the null is true. With confidence intervals, we're doing bootstrap sampling because we want to know what the standard error is. With hypothesis tests, you're always wanting to know what's the distribution of values when the null is true. And so there's 2 ways to do that as well. And one is the randomization test via simulations. And that's, again, where we, in a sense, reshuffled the values and reassigned the outcome of interest to different people, which would basically say the outcome that we're interested in isn't affected by the independent variable that we're looking at, creating a scenario where the null hypothesis is true, and then you run that simulation 1,000 times to sort of get a distribution of what the value of the test statistic would be when the null is true, or when there's no effect. So you directly simulate the test statistic we would observe just by random chance if the null is true. Then the other way, again, there's certain properties such that we kind of know what the distribution of test statistics would be if the null is true. It's going to typically follow a normal distribution. That's why we can use formulas to calculate a p-value for our hypothesis test. And that's where we use the formula to calculate the test statistic based on its theoretical distribution when the null is true. So for the second half of this class, what we've been doing is the formulas. So really, a lot of the tests that we did in the first half of the class, where you just sort of look at the bootstrap sampling distribution, or you look at the randomization sampling distribution, you just look at it and you find the middle 95%, or you find the proportion of values as extreme as your test statistic. With the second half of class, what we've been doing is using the formulas to obtain the p-value for our test statistic. There's some benefits to bootstrap, to the simulation methods, and there's some benefits to using formulas. Conditions where you would be constrained in which options you can use. If the sample size is small, you have to use the simulation methods because the theoretical distribution, it doesn't meet those conditions. And if the sample size is large, you can use whatever method you prefer. They're both going to produce the same results, more or less the same results. So it's redundant to use both methods unless you want to check your answers and make sure that you're doing okay. As far as accuracy, the more simulations you do, the more accurate of a response you'll get. So that's why we do like 1,000, or you can even do 10,000 or more. When you're using formulas, the accuracy is affected by the sample size. And you'll notice, like in all the formulas, as the sample size n increases, the standard error is going to go down because you have more information. So if a bootstrap sampling distribution is approximately normally distributed, what's the notation that we'd use to describe the bootstrap sampling distribution? A lot of the second half of the class has been doing inference, which is confidence intervals and hypothesis tests. And so this is the formula that we've been using, and then this is for hypothesis testing. So this is a core formula, but it changes for every type of scenario where we have a single quantitative variable or a single categorical variable. So it's good to know this, but the only one that you should know is 2 standard deviations away from
2 and 2.
Yeah, that's the only thing that I would expect you to know. These are the core formulas, but it's critical that you know how they are adapted for each scenario. And this is why with bootstrapping, you don't have to do any of these formulas. The computer will simulate it, and so that's why a lot of people would prefer bootstrapping, just simply because it's intuitive. You see what the actual distribution of values are. Whereas this, you're kind of like, okay, now what type of variable am I working with, and what am I testing? So you have test statistics, and I think we've hammered this in, but a test statistic is the observed sample statistic you use when conducting a hypothesis test or a confidence interval. So whenever it talks about test statistic, it's the statistic that the value of your sample that you're most interested in, that you've calculated from your sample. With hypothesis tests, you're testing to see how unusual it would be to get this value by random chance if the null was true. So, and then through the hypothesis test, you determine the probability of getting a value as extreme as your test statistic when the null is true. The first half of the class, we just simply would get a test statistic, and the value would just be some random value that I'll say was unstandardized, and so you couldn't really compare one test statistic with another. But then what we learned was you can take whatever your test statistic is and standardize it so that you can easily and quickly compare it to other test statistics or to the different distributions that we have. And so that's when we transitioned to always doing the standardized test statistic, and that's the Z statistic and the T statistic. It basically takes whatever your test statistic is, so like if your sample mean is 6, then it standardizes it. The way it does that is by subtracting the null value, which often is 0, and dividing by the standard error. And the standard error is the thing that we're looking for, is the thing that either we can get through bootstrap sampling distribution or through the formulas. The z statistic is the number of standard errors, and observed sample statistic is from the null value. So it's when we learned z-scores, this is an application of that, whereas you have your test statistic, and when it's standardized, you know if it's more than 2 standard deviations from the mean, then it's going to be greater than the 5% threshold. So that's why you can kind of know if your standardized test statistic is greater than the value 2, it's probably going to be significant, because all of them have been standardized so that you can compare them across each other. So you're basically converting whatever your test statistic is, a standard number. So if you're doing a study on attitudes about homosexual activity, you'll get a t statistic for a variable that's 4.8, and when McKay's doing her study on happiness, she's going to get a t statistic for a variable that's 5.6. Even though you're studying completely different things, we've standardized our test statistics. So, or let's say that both of you are looking at happiness as an outcome, and you were looking at marriage as a function of happiness, and McKay was looking at age as a function of happiness, and your t statistic was 48, and your t statistic was 3. That allows you to compare, like, wow, she has much, much stronger evidence that marriage is associated with happiness, whereas yours is evidence that where we would reject the null, but it's not nearly as strong as what she has. So that's where the standardized test statistic puts it into a standard number that can be compared across tests. One thing to note on your review slides, which isn't in there, which you'll need to add, is I gave you the chart of all the different ways to calculate the standard error for each of those scenarios. What I didn't do was put in what the estimation of that is. So on the chart, what I noticed was it has P, which is the population proportion, and it'll have mu, which is the population mean. And the values that we're estimating the standard error to be is our sample proportion. So you just want to make sure, just don't say, oh, I got all the formulas, I'm set. You kind of need to know, I typically won't have the population proportion, but I know that a close equivalent to the standard error, our best estimation of it is using the sample proportion. And this just illustrates increasing sample size decreases the standard error. So this shows you visually, if you just have a sample size of 10, you have this level of standard error. But if you increase it to 100, standard error goes down, and then 1,000, and so on. It'll continue to pull the amount of uncertainty you have about your test statistic down lower and lower. That's why, like with the GSS, some of you have sample sizes of 50,000. So your standard error is super, super low because they have tons of information in that data set. And what I want to do for the second part here is actually go into the GSS and run some of these tests. McKay created a variable on here. Maybe her tutor helped her some. But it's called happy1, which basically takes the variable that we've been looking at called happy and puts it in an intuitive order. So the value 1 is related to being not happy, the value 2 is related to being somewhat happy, and then 3 is very happy. So as the value of the happy variable goes up, happiness goes up. This is what's called an ordered categorical variable, and it's a helpful variable because it can be treated, when needed, it can be treated as a quantitative variable. So 1 means little happiness, and 3 means an increase in happiness. So there's a trend to the categories. So this is the proportion of people, this is a categorical variable, and we want to find the confidence interval for the proportion of people that are very happy. How would we do that? Do you have an idea, Chris? Give me the formula first, just so I can...
Sample statistic plus or minus Z star times standard error. And that is equal, do you want me to tell you the other real proportion, or like what it's equal to? So like sample proportion plus or minus Z star times square root of that one.
So it would be P hat,
Yeah, P hat.
plus or minus. And then we want the Z star time, and then what's?
Yeah, it's the square root of the P hat, and then parentheses 1 minus P hat, and then divided by N.
Is the square root over the whole formula, or just the?
Yes.
And then let's plug in the numbers for 95%. We want the proportion. So we know that there's 50,423 people in the sample, and we know that 16,784 are very happy.
So wouldn't it just be the proportion be 33.3? Because that's the proportion of how many people are happy.
But a thing to remember, a proportion, all the proportions added together will equal 1. So the proportion for this, for very happy, would actually be 0.33. Because if you put in 33, your number is going to be off. So we have 0.33. If you notice right here, it says column percent. It says the cells contain column percent and weighted N. You could do the math if you wanted to, or if you are familiar with interpreting these tables, then it can help you. So 0.33 plus or minus, and it's 95% confidence interval.
2?
So what is N? Sample size. So what's the sample size of this?
50,420.
Okay. Yep. What we're actually looking at is what's the proportion of the sample that's very happy. It would be incorrect to pick the N of just that group. 16,000 is the number of people that are very happy, whereas 0.33 is the proportion. And then you could do the math to calculate that out. Because this is an ordered categorical variable, the summary statistics have meaning. The mean and the median and the mode, you can actually interpret them in a meaningful way. And so if we look at this and we want to know what's the average level of happiness for people in America, how would you answer that just looking at this? What's the mean value for the distribution of values on happiness?
2.
Okay. What does that mean in light of the variables?
Majority of the people are somewhat happy.
We're talking average. Majority sounds more like proportion, right?
Yeah.
So what's the average happiness level?
Somewhat.
It's actually, because it's 2.22, it's between somewhat happy and very happy. A little bit more than somewhat happy. This is important to understand because a lot of the variables that we're working with are ordered categorical. And so that's the way that you would interpret it, is you look at the mean, it says 2.2, and then you go back up to your variables and you're like, okay, where does that fit on that continuum? If we wanted to calculate the confidence interval for the mean level of happiness for people in the US, how would we do that? So we have our point estimate of the mean level of happiness, which is 2.2. What's the confidence interval for that point estimate? How confident are we that the average American is 2.2 on the happiness scale? In a sense, I could ask a question that says, what's the confidence interval for a particular proportion? Or using the same variable, because it's an ordered categorical, I could say, what's the confidence interval for the sample mean? And if I ask for what's the sample mean, I'd want it to be interpreted. It isn't helpful to just say it's 2.2, but it's basically saying the average person is between somewhat happy and very happy. Because if I say, what's the happiness level of the average person, if you just said 2.2, I'd be like, what does that mean? You'd have to say, it's between somewhat happy and very happy, is the interpretation of it. So that's with single proportions, single means. If we expand it and we say, we want to look at happiness, and let's also look at race. And we're just going to be interested in black and white people to make it statistically simple. This is an example of two categorical variables, but this variable happiness has a unique feature where it can actually, if needed, be treated like a quantitative variable. So then If I asked you guys, what proportion of very happy people are black?
So it'd be 1,470 divided by 14,833.
Yes. So this is important, and this is, I think even on the first exam, people got tripped up. So we want to know the proportion of very happy people who are black. A way to think about this is the population that we're starting with is the total number of very happy people. So that's why it would be 14,833. And then we want to know what proportion of these people are black. So you divide 1470 by 14,833. So then if we wanted to look at what's the difference in proportion of white people who are happy compared to the proportion of black people who are, we'll say, not happy. Let's see. So the difference in proportion of black people who are not happy compared to white people, the proportion of white people who are not happy. P hat, white people not happy minus P hat, black people not happy. So the proportion of white people who are not happy is 0.096, whereas the proportion of black people who are not happy is 0.199. So the difference in proportions is negative 0.13. So this is a point estimate for the difference of proportion of black people who are not happy compared to white people who are not happy. For difference in proportions, the key thing, like P1 would be the proportion of white people who are not happy, N1 would be the number of white people, P2 would be the proportion of black people who are not happy, and N2 would be the total number of black people. The same would be if we wanted to do a hypothesis test using the same process. If there was a theory out there that said black people, because of structural inequalities, black people carry a lot more psychological constraints just because of the greater pressures and obstacles they face, so they're going to be, on average, less happy than white people. So this is where it might get a little tricky, is say there's a theory out there that says that on average, black people are just going to be less happy than white people because of structural inequalities that sort of are biased against black people. So we want to test that hypothesis. How would we use this data? What's the mean? Because this is an ordered categorical variable, you can say the mean level of happiness for white people is 2.25. The mean level of happiness for black people is 2.04. And so then you can do a hypothesis test that looks at the difference in means between white people and black people. So then the last one that I want to walk through is where we do the regression of the same thing. So this is the regression. So this is basically saying in what way is race, being black or white, associated with happiness. And what it's saying is that race is negatively associated with happiness. And what that's saying is going from a 1 unit increase in race leads to a decline in happiness. And so if you think about it, the first unit that we're looking at is white people, the categories. And if you do a 1 unit increase in the category of race, which means going from white to black, the happiness level drops by negative 0.21. But what you would need to do is be able to write the regression equation for the relationship between race and happiness. An example where I would probably be better than using race, we'll say education. If I said a person had 1 unit increase in education, how much would their happiness increase? Or if I said, if someone has 15 years of education, what's their predicted happiness level? This is stuff that you're doing for the final project, and it's helpful to know how to interpret what you're seeing on GSS. So if you're going to focus on things, it would be the exercises we've done with the GSS.